In a redundant network, a single point of failure may be a switch failure or a cable failure. Usually, a network distribution layer, you need multiple switches so that you can minimize the chances of failure. But when you introduce multiple switches in a network, there are drawbacks. Two, there may be loops and duplicate frames, which has very severe consequences to the network. So, to prevent this loop and duplicate frame, spanning tree protocol has been developed. Spanning tree protocol runs on spanning tree algorithm. This spanning tree algorithm designates a single switch as the root bridge and use this switch as a reference point to calculate the best path while blocking the other path. You can see in this animation video to comprehend how STP choose to block the path. In this video, you'll see that the PC1 sends the broadcast out onto the network. Switch 2 is configured with STP and has set the port for trunk to a blocking state. The blocking state prevents ports from being used to forward user data, and this prevents loop. Switch to forward a broadcast frame out all switch port except the originating port from PC1 and the port for trunk 2. Switch 1 receives the broadcast frame and forward it. Switch 1 receives the broadcast frame and forward it out all of its switch port where it reaches PC4 and switch 3. Switch 3 forward the frame all of its port fast Ethernet 0/2 because it cannot forward fast Ethernet 0/1. This is the originating port because switch forward all the frames except the port it has received. And when the switch 2 receives this frame, it drops because this trunk has been blocked. This is the blocking port, and this is how the switch 2 prevents the loop from forming. Now you take a look at the video. PC1 is sending a frame to switch 2, and switch 2 forwards the broadcast out all port except originating port and the block port. Now S1 forward the broadcast out all port except the originating port, and S3 receives the frame and forward it now in this pictures you're going to be seeing STP recalculating when a failure occurs. The trunk link, which is S1, the trunk link between S1 and S2 has failed. This has failed. S2 unblocked the ports. You will see that the S2 unblocked the ports for trunk 2, and then PC1 sends a broadcast frame to S2. S2 forward out all of the port except the originating port. It forward here and forward here, but it only do not forward this port, and failed link for the trunk. Sorry, the PC1 is not going to be forwarding this one because this is a failed link. Now S3, once it receives, forward broadcast out all available port except the originating ports. It receives here, and it is going to be forwarded out this way because it cannot forward out this way. This is the originating port. And now S-word forward broadcast only out fast Ethernet 03. It cannot block this way because it cannot forward is this way because this is a blocked port. Now let's play the video. Now, how STP select a root bridge and block other ports? Root bridge is selected through a participation process. All switches that are participating in STP exchange BPDU frames to determine which switch has the lowest bridge ID or BID on the network. The switch with the lowest BID automatically becomes the root bridge for the STP calculation. Now let's discuss little details about BID and BPDU. Now spanning tree algorithm depends on exchange of BPDU to determine a root bridge. A BPDU frame contains 12 distinct fields that convey the path and priority information used to determine the root bridge and the path to the root bridge. There is a 12 field here. The first 4 fields identify the protocol versions, message type, and status flag. The next four fields are used to identify the root bridge and the cost of the path to the root bridge. And the last 4 fields are all timer field that determines how frequently BPDU messages are sent and how long the information received to the BPDU process is, how long the information received to the BPDU process is retained. As the switch forward their BPDU frame, adjacent switches in the broadcast domain read the root ID information from the BPDU frame. If the root ID from a BPDU received is lower than the root ID on the receiving switches, then the receiving switch updates its root ID, identifying the adjacent switch as the root bridge. Now, in the first picture shows a spanning tree instances, where a switch designated as a root bridge. The root bridge serves as a reference point for all spanning tree calculation to determine which redundant paths to block. An election process determines which becomes the root bridge. Now, in the second pictures, it shows that the BID field. The BID field is made up of a priority value and an extended system ID and a MAC address of the switch. Now, BPDU frame lowest BID ends up being identified as a root bridge. So, if a priority value is the lowest in a BPDU frame, that identifies being as a root bridge. The lowest priority value that root bridge is for that spanning tree instance only. The lowest priority is the lowest BID, which with the lowest priority value becomes the root bridge. The lowest priority actually takes the precedence. So if you want a switch to become root bridge, set the priority value as the lowest. The bridge priority is range from 0 to 61,440, and it is incremented from 0 by 4096, such as 0, 4096, 8192, and so on. A bridge priority of 0 takes the precedence over all other bridge priority. Now the extended system ID. A BID has a 2 byte of 16-bit value field, 4 bits for the bridge priority and 12 bits for extended system ID. This 12-bit identify the VLAN participating in this STP instance. You can see rightmost 12-bit for VLAN ID and leftmost 4 bits for bridge priority. This explains why bridge priority value is configured 4096 increment, because 2 to the power 12 is 4096. So the VLAN in the BPD frame is the 12-bit value in the state extended system ID. The 4-bit bridge priority value and 12-bit extended system ID is called BID. When two switches are configured with same priority and same extended system ID, now switch with the lower MAC address then will be determine the lower bridge ID, and the switch with the lower MAC address in this instance become the root bridge. Now in this picture, in the second picture, we see that S1 has a lower priority than the other switches. S1 is a 24577, and this one is a 32769. This one is 32769. So S1 has the lower bridge priority, and therefore it becomes the root bridge. The spanning tree select this one as a root bridge. And in this picture, you see that when all switches are configured with the same priority value, this one has the 32769, this has a 32769, 32769, and a default priority value configuration is 32768. Since every switch is a one path away, this is one is added to 32768 and becomes 32769. So all three switches has a default priority value of 32769. So the MAC address will become the deciding factors. So MAC address for switch 2 is the lowest one. It has a 111 value as the last digit. This is 333222. So this is the lowest MAC address, and this become the root bridge. Now, after the root bridge has been determined, the STA, which which is spanning tree algorithm, calculates the shortest path to the root bridge. Each switch uses spanning tree algorithm to determine which port to block, while spanning tree algorithm determines the best path to root bridge for all switch ports in the broadcast domain. Traffic is prevented from being forwarded to the network. Spanning tree algorithm considers both path and port cost when determining which ports to block. The path costs are calculated using port cost value associated with port speeds for each switch port along a given path. The sum of the port cost value determines the overall path cost to the root bridge. If there is more than one path to choose from STA, from spanning tree algorithm, choose a path with the lowest path cost. Now in this picture you see the default port cost. The default port costs are defined by the speed at which the port operates. You see the 10 gigabyte Ethernet port have a port cost of 2. 1 gigabyte Ethernet port have port cost of 4, and 100 megabits per second Ethernet ports have a port cost of 19, and 10 megabits per second ports have a port cost of 100. So as the speed decreases, the port cost increases. Although switch have a default port associated with them, the port cost is configurable, and an administrator can configure the port cost and control spanning tree paths to the root bridge. Now to configure the port cost of an interface, and you simply use spanning tree cost command in the global configuration mode, and in the interface configuration mode, and then you type what is the port cost that you want to set. In this instance, we set the port cost 25, but port cost could be we can use from 1 to 200 millions to set the 1 to 200 million and this is the range that we can select as a port cost. In this example, switch port fast Ethernet 0/1 has been configured with the port cost of 25 using the spanning tree cost command, and it is on the fast Ethernet 0 interface. Now if you want to restore the default value, which is 19, you simply need to enter no spanning tree cost. This will restore the default value of port cost 19. Now in this example, the path cost from switch 2 to root bridge S1 over path 1 is 19, which is the default value, while the path cost over path 2, this is the path 2, is 38, because this is going to be 19 and another 19, so this is 38. Because path 1 has a lower overall path cost to the root bridge, it is preferred. A spanning tree protocol configures path 2, which is redundant path, to be blocked, and this is how STB prevents a loop. So the path cost is equal to sum of all port cost along the path to the root bridge. Path with the lowest cost become preferred, and all other redundant paths are blocked. Now to verify the port and path cost to the root bridge, enter the show spanning tree command. The cost field near the top of the output is a total path cost to the root bridge. This value changes depending on how many switch ports must have traversed to the root bridge. In the output, each interface is also identified with an individual port cost of 19.